We've learned that isotopes are different atoms of the same element. Isotopes of an element will have different masses because they differ in their number of neutrons. We also know that most elements have at least two isotopes, and that those isotopes exist in different abundances. And those abundances can vary wildly from element to element. Now, we'll elaborate on those differences in relative abundance and what it means for our calculation of average atomic mass. This will be our first big calculation for the term, and I'll approach explaining the calculation in this video in a different way than I explain the calculation in a later video. If one makes more sense to you than the other, pair the explanation you like with the values from the opposite video to ensure you get the additional practice. We'll start with a slide that I promised you would see again later. In the earlier video, it was just meant to provide a visualization to show that different elements have different isotopes that occur in different abundances. Now we're going to use it, or really parts of it, to discuss what the average atomic mass does and why we have to calculate it a certain way. We'll start our conversation with our old friend carbon. The different colored areas on this pie chart here each represent both an isotope and that isotope's percent abundance. As a reminder, carbon has three naturally occurring isotopes, the masses and percent abundances of which are given in the table here. For clarity, let's elaborate on the percent abundance values for a moment. We'll use percentages a lot in this term and next term, and each and every one of those percentages can be narrowed down to a part over a whole. Percent is a particularly useful whole because it takes our parts out of 100 parts. Each of these gray circles represents one single part, and the grid is 10 by 10, so there's 100 parts total. Now let's start with carbon-13. Rounding down, this roughly 1% means that for every 100 parts, or my gray circles, exactly one of them is going to be carbon-13. The other 99 will be attributed to carbon-12. Carbon-13 atoms will make up one part of the 100 total parts, and carbon-12 atoms will make up 99 parts of the 100 total parts. Any elements that's specifically listed with the word trace isn't going to be included in your calculations. Trace elements are kind of like the fruit flavoring in a LaCroix. A grapefruit flavored LaCroix, for instance, tastes like it sat in a room with a grapefruit. You know the grapefruit existed, but it's not actually measurable in the drink. Think of trace elements as being known to exist, but so difficult to measure that we can't quantify them well. They're our atomic equivalent to LaCroix's inedible grapefruit. Do be super careful here though, because chemistry instructors love to give you 3 isotopes and only 2% abundances for our non-trace elements. That's because you can always figure out the third percent abundance because, since our parts are percentages, they have to add to 100%. An element specifically has to say trace to be eliminated from a calculation. If you aren't sure whether you should include a value, subtract what you do have from 100. If the difference is more than 0.01%, you really should include that isotope in your calculations. It is very easy to be tempted to take simple averages of the masses of these two isotopes that exist for carbon, given that the term average atomic mass exists. The problem is that simple averages, simply adding the isotopic masses for the isotopes and dividing by 2, would give both carbon-12 and carbon-13 even say in what the resulting atomic mass of a sample of carbon would be. Both the pie chart and the grid of circles pretty clearly shows that this shouldn't be our play though, because there's nothing even about the distribution of the isotopes for carbon. Instead, our math needs to agree with our pie chart, or in other words, it needs to say 1 out of every 100 atoms will have a mass of 13.00336 AMU, and 99 out of every 100 atoms will have a mass of 12.000000 AMU, and the atomic mass of the sample will be the sum of those pieces. The resulting equation looks something like this. You multiply the percent abundance of an individual isotope, reduced to fraction form, by the atomic mass for that particular isotope. You'll do this smaller calculation for each measurable isotope of your element, meaning if you have 7 known isotopes that aren't listed as trace, as is the case for molybdenum and a handful of other elements, then your equation will be the sum of these 7 smaller contributions. Note that to reduce a percentage to a fraction, you simply divide that percentage by 100%. Your final answer for the average atomic mass of an element will be somewhere between the atomic masses of the isotopes given. If you happen to forget to use the abundance in fraction form, you'll know because your answer will be 100 times bigger than it should be. which will be nowhere near the numbers given in the problem. Now let's work through how to find the average atomic mass for carbon. Elements are great ones to practice with because we can turn to the periodic table and find the correct answer. This gives us a target to work towards, which is always good. There's a PDF in the middle of the content page that has atomic masses and percent abundances of a few elements so that you can practice these calculations. The first thing you'll want to do with these problems is make sure your information is organized. Now, I already have it in table form here, so in this case, we're good to go. In the word problems found later in the page, making something similar to this table where the atomic mass and the abundance for each isotope are paired up will make plugging the values in a lot easier. As a reminder, we will need to figure out how much of the pie is carbon-12 and how much of the pie is carbon-13. Since the abundance of carbon-14 is listed as trace, it doesn't get a piece of our calculation pie. One of the biggest places students trip up on these calculations is pairing the wrong values. So again, always double check your table before you begin your substitutions. Once you know you're good to go, replace the abundance variables with their actual values and replace the atomic masses with their actual values. The first term in our equation equates to the green portion of the chart. It should be a much larger value than the second term since the green portion of the pie chart is much larger than the purple portion of the pie chart. Now, a couple things of note at this point. Since there is a percent in the numerator and the denominator, that percent will cancel. This leaves us with the fraction form of percent abundance. Also, notice that I included every one of the very many decimal places from the table for the atomic mass, and you should as well. Once we've calculated the average atomic mass for the element, we'll be able to round, but we want to represent our sample as accurately as possible, so we're going to use all of the significant figures that were given to us. Now, simplify your expression, meaning calculate the contribution of the first term, which is the larger section of our chart, and then figure out the contribution of the second term, which is the smaller section of our chart. If you're gifted at using parentheses in your calculator, you can skip this intermediate step. But these two values are the products for each of our terms. Now, to determine the average atomic mass, we simply sum these two pieces. We can confirm whether our calculation is plausible here by looking at the periodic table. We have the exact value given for carbon. Woot! This is our first major calculation of the term. There can be a ton of moving pieces with this one, depending on how many isotopes your element has. Reorganizing information will help keep track of all of those moving pieces.